আচ্ছা দাদা, যদি তানভীর ইসলাম প্রথম থাকে তাহলে আপনারা শুরু করে দিন। 10:30 বেজে গেছে।
হ্যাঁ,
ঠিক আছে।
আচ্ছা আচ্ছা, ঠিক আছে। ওকে। Okay, welcome to ICTEMA 2020 to be held at which being held at Jalpaiguri Government Engineering College. I am Madhav Chandra Mandal, Assistant Professor from Jalpaiguri Government Engineering College. I am the session co-chair of this conference, and our session chair, Professor Jagabandhu Seat. He is HOD of Mechanical Engineering Department from Purulia Government Engineering College. So our session chair, Sir Professor Seat, kindly proceed for this conference. Thank you.
Okay, thank you very much and very good morning to all of you. And thank you very much, Madhav, for your kind introduction. Okay, and let us, we are going to start the important session. The session which is actually under the theme of thermal engineering and management services at international conference conducted by Jalpaiguri Government Engineering College. I would like to indicate that I am very much pleased and honored to be invited to chair this important session, where the session comprises most probably 6 papers. Session consists 6 papers. Now, before actually starting the session, actually we should adopt some rules. Rules means regarding time allotment. Every presenter would be given 10 minutes. 10 minutes time slots of presentation, and for questions and answer session, extra 3 minutes will be provided. With this, at first I would like to welcome the first presenter who would be making a presentation on the topic thermal and rheological behavior of a wax-based binder and an alumina feedstock for micro PIM application, where this paper will be presented by SK Tanvir Islam, Department of Mechanical Engineering, Jadavpur University. Okay, I am requesting Mr. Tanvir Islam to continue with presentation. Okay, so Tanvir, please.
I'm Sheikh Tanvir Islam. I'm going to present our work on thermal and rheological behavior of a wax-based binder and an alumina feedstock for micro PIM application. For a brief description of the powder injection molding, we can see here a schematic diagram, and there is 4 stages. First one is mixing, second one is injection, third one is debinding, and fourth one is sintering. At first, in mixing stage, powder and binders are mixed together. Then that mixer is called feedstock, and feedstock is feeded into injection molding machine to give it a shape. Then that compact is sent for debinding, and where the binder is removed from the compact, and then it goes to sintering process, where particles are joined and to give the strength to the component. And micro powder injection molding is just like this one with a manufactured form of conventional powder injection molding. The objective of the current work are as follows: to design a wax-based binder having shear thinning behavior then thermal and rheological characterization of the binder, and an alumina feedstock using the same binder predict some basic process parameters from the characterization data. Here we have used thermally reactive alumina powder due to its low sintering temperature, and as a binder we have used paraffin wax and low density polyethylene. We can see here from the graph that for this particular powder binder combination, we found it is 49% of maximum powder loading could be provided, and that is called critical powder loading. And that's why we have taken a 45% powder loading feedstock for our further experimentation. TG analysis. Here, loss of weight is recorded with increasing temperature, and we found that at 193 degrees centigrade, the feedstock starts degrading, and above 478 degrees centigrade, there is no change of weight loss. That means there is no such binders present in that feedstock to degrade. DSC analysis. In this case, from DSC analysis, we can found the melting and solidification points of that binder and feedstock as well. And from this DSC analysis, we can calculate the specific heat and latent heat of solidification, as it is more important than liquid than melting of our binder. Here we have calculated these values. Then thermal conductivity measurement. In this process, in this case, we have used flashlight source method to measure the thermal conductivity of the binder, and for a wide range of temperature. During our injection, the temperatures falls from higher to lower. That's why we measure this in that way. Rheology analysis. Rheology analysis shows us the flow behavior of the material, and here we analyze that flow behavior of binder as well as feedstock. And here two graphs are presented here for the binder at two different temperature level. First one is at the higher temperature where binder is completely liquid, and second one is temperature is such that one of the binder ingredient starts solidified. Here we have used a modified cross model to fit these graphs, and from these two graphs we can see these are shear thinning. They have a shear thinning behavior. With increasing shear rate, viscosity is dropping. Similar kind of experiment has carried out for the feedstock, and we found here also a shear thinning behavior, which is favorable for injection molding process. And we from the model we have used earlier, that is modified cross model, and we found a power law index for liquid binder is 0.91, semi-liquid binder is 0.32, and for our feedstock it is 0.43. It is found that there is a significant difference between liquid binder and solid binder, semi-solid binder. So this is due to so it means that semi-solid binder highly dependent on shear. Microchannel out of alumina. We have prepared a feedstock, alumina feedstock, and then we injected it into a dye. That is their microchannels are made on that dye, and we have two samples. One is injected one, and second one is sintered one, and that component is dewound at 500 degrees centigrade and sintered at 1540 degrees centigrade for 30 minutes, and we achieved 97% of density of the alumina. And this component could be used for cooling purpose in small devices. Conclusion of our work is TG and DSC analysis suggested that the injection temperature should be in between 92 degrees centigrade to 193 degrees centigrade, and wax-based binder system provides a shear thinning behavior to the feedstock. A modified cross model fits the rheology data. Data like latent heat and specific heat obtained from DSC analysis and flow behavior of the binder and feedstock could be used to simulate the injection stage in future work. The applicability of the feedstock A55 A45 is in micro power injection molding is experimentally validated by developing micro channels by injection molding and subsequent debinding and sintering. Here are some references we have used. Thank you.
Is it over?
Yeah, it's over.
Okay, now I am requesting to audience, if there is any questions, then we can raise the questions. We can ask the questions to the presenter, Mr. Tanvir Islam. Okay, now Tanvir, I would like to ask one question. Okay, do you have actually numerical part of your paper?
I am not presenting it this one with this paper. I'm only using only characterize this data, characterize this feedstock and binder to collect data.
Only by collecting data you have analyzed this paper.
Yeah.
That means you have not done any experiment as well as you have not done any numerical simulation as well as validation.
I have done experiment to find out this data, and after that I will use this data to simulate that process, injection molding.
Now you have done your experiment from actually which lab? Jadavpur University.
I'm not using Jadavpur University facility. I'm using CSAR CMERI Durgapur facilities.
Okay. But nowadays, actually, only experimental part will not fulfill the purpose. You have to always.
Yes, sir. I'm doing a simulating part also, but this paper does not does not have that part. That's why.
Okay. So you are having plan to continue the same for simulation.
Yeah.
Okay. Probably there is no questions from the audience. Okay, we can proceed for the next presentation.
Okay. Thank you.
Okay. Thank you. Now, actually, next presenter, I don't know. Actually, it is not provided to me the name of the next presenter. Okay, but I am actually requesting the next presenter who will be making this presentation on the topic modeling of laser forming process using finite element method. A review. Whether anybody is present to present this paper. Anybody is present to present this paper? Having paper ID MM1560, where Sidnangshu S. Chakraborty was the first author. Sidnangshu S. Chakraborty from Material Processing and Microsystem Laboratory, CSIR, Central Mechanical Engineering Research Institute, Durgapur. No one is present. No. Okay. So leave it. We are proceeding for the next paper. Okay, having paper ID MM1561, and title of the paper is Deposition of Duplex and Multi-Layer Electroless Nickel NIB coating and study of their oil resistance. And probably this paper which will be presented by Mr. Polas Biswas, Department of Mechanical Engineering, Jadavpur University. So I am requesting Mr. Polas Biswas to present your paper. Okay, Mr. Polas Biswas, please. Palas Biswas, are you there? Palas Biswas, are you there? Probably I have seen just few minutes back he was present. Probably he is not there. Now he is not available. Okay, probably there may be a problem of connectivity, network connectivity. Okay, so if he comes again, then obviously we will uh, give him chance to present his paper. Okay. Now, as he is not present, so I am going for fourth paper. Having paper ID MM1561, and the title of the paper is Deposition of Duplex and Multilayer. No, sorry. Having paper ID MM1566, and the title of the paper is Finite Element Modeling of T-casting Process and its Validation on AISI 4340 Structural Steel Plate. Where the paper supposed to be presented by Mr. Sudhir Kumar, School of Engineering and Technology Department, Central University of Haryana, and Department of Metallurgical and Material Engineering, Indian Institute of Technology, Roorkee. So I am requesting Mr. Sudhir Kumar to present your paper. Mr. Sudhir Kumar, please. Are you there? Are you there? He is also absent. He is also not there. Okay. Sudhir Kumar, are you there? Probably he is also absent. Okay. Now let us go for fourth paper. Having paper ID, paper number 5. Having paper ID MM1570. The title of the paper is Effect of Process of Parameters on Force Trains During Friction Stir Holding of AISI 316L pipes. Where the paper which is supposed to be presented by Suresh Gayan, Department of Mechanical Engineering, Jadavpur University. So I am requesting you, Mr. Suresh Gayan, to present your paper. Suresh Gayan, are you present?
Yes, sir. Yes, sir.
Okay. So we can continue for presentation.
Okay, sir. Okay. Just for 1 minute, I am sharing my screen.
Okay, no problem at all. Suresh Gayan, is there any problem, Suresh? Suresh Gayan, is there any problem? Probably they are maybe having the problem of network connectivity. Suresh Gayan, we are able to get you. Suresh Gayan, he has joined the meet, but we are unable to get him actually. Suresh Gayan, not responding. Suresh Gayan, you are not responding. Polas বিশ্বাস is there? Polas বিশ্বাস?
Yes, sir. Yes, sir. Sir, College business is available, sir.
Okay, okay. So as Suresh Gayan, actually we are unable to connect with him. Okay, so I am requesting, as I told just few minutes ago, the topic of this paper. Okay, again, sorry, Polas Biswas, again, I am asking to present your paper, where your paper title is Deposition of Duplex and Multilayer Electroless NIB coating and study of their oil resistance. Okay,
Okay,
so
okay, sir.
you can continue for your
Yes,
for
yes,
this
sir. Yes,
presentation. Okay.
yes, yes, sir. Yes, sir. 1 minute, sir. Sir, my skin is visible.
Okay, it is clearly visible. Okay.
Okay, sir. Okay, sir.
Now
Okay,
you
sir.
can proceed. No problem
Yes,
at all. Okay.
yes, sir. Yes, sir. Good morning, everybody. My name is Palaj Vishwas, and research scholar in Jadavpur University, Department of Mechanical University, and also my co-author is Dr. Suman Gollan Das and Dr. Prashanto Shah, and I am presented on this paper, that is the deposition of duplex and multi-layer electrolysis NIB coating and the study of their wear resistance. And a few key points about that. That is, the electrolysis deposition method is carried out by a chemical reduction process, which is reduction of metal ions through autocatalytics away from aqueous solutions contained with the reducing substance, stabilizers, and operating in a specific, and also the pH value and temperature have some maintained according to your the coating deposition time. And also the electrolysis deposition coating, that like your the duplex coating is the very slow rate here. And electrolysis deposition method has experienced more popular for industrial applications due to excellent tribological, electrical, as like as mechanical and physical properties. And also, this will be applied for the whole type of industry like that, or it's in daily uses equipments like or in a very simple example, in our Almira is also used like that here. And producing homogeneous coating with the electrolysis deposition is possible with also exhibits high quality addition on different substrate materials. Like that, electrolysis process allows producing very uniform homogeneous coatings. Like that, your the properties of developed coating components, deposition state and structural nature predominantly depend on plating, bath conditions and compositions also. And to increase the corrosion resistance, the alloying elements like the zinc, molybdenum, copper, etc. is added with the electrolysis, that is the NIP and NIB coating. That is the different type of the nickel phosphorus as like as the nickel bronze coating can be included about this type of components. And a few researchers are not fully convinced with the progress of corrosion resistance of the deposition coatings here. For this, considerable attention has been paid. That is the duplex coating. That is the NIP as inner layer, as like as the NIP is considered according to your the outer layer coating as well as multi-layer coating deposition. That means the not is the duplex coating. That is the more than two layer of coatings can be creating like that your the multi-layer coating deposition, which includes all types of mechanical and tribological properties improvements. Another here, the alternative methods of coating are investigated to prepare multi-layer electrolysis nickel coatings to monolayer coatings. The wear rate is very low in the duplex coating, and present works, that is your the objective of the present works. The present works involves with the preparations of duplex NIB by NIB. That is the NIB is the inner layer, and as like as the NIB as a outer layer. And the both process also you can done during to this investigation. Like that, the NIB is creating, that is your the inner layer, and also the NIB as the outer layer is coating deposition in the duplex coatings. And another things like that, your the multi-layer coatings, the NIB and NIP, that is your the four successive layer is done during to your the coating deposition process. Like that, the NIB as a inner layer, as like as the NIP as a outer layer, and also coating using dual bath techniques. These are also evaluate tribological, like that your the like wear resistance, coefficient of frictions, and mechanical properties, that like your the micro hardness can be measured during to here. And this is our the experimental procedures, as like as your the first we can prepare the sample preparations, and also the sample preparations about that the simple mild distilled substrate is used, and this is the AISI 1040 grade is of mild distilled is used. And also the two type of sample is preparations about that. The one is the square sample, and the another is the pin sample. And the square sample dimension is given, that is your the 15 into 15 into 2 millimeter. This is the for characterizations of that, that is your the square sample, that is your the measured for your the microstructure, like that your another hardness values, and also the cylindrical samples is used for your the tribological test. And firstly we can prepare like that your the samples, and also that is the grinding the more times about that. And also the we can firstly cleaning about your the rust from the these samples, and also this will be deposition for 1 minute, that is the hydrochloric acids solution, like that the 50% solutions. And then this will be put in the 1 minute, and after that completion of your the sample preparation, then this will be submerged in your the previously prepared the nickel bath nickel bronze bath solutions. Okay, and this is the nickel bronze bath is prepared, like that the different component is used, like your the nickel chloride, sodium brohydrates, the ethylene diamines, and the lead nitrate, also the sodium hydroxide is used. That is the prepared for your the nickel bath. And also the different composition, the amount of here, that is the nickel chloride is used for the 20 gram per liters, and the sodium brohydrate also used for the 0.8 gram per liters. The ethylene diamine is used 59 gram per liters, and the lead nitrate is used for the 40 gram per liters, and also the sodium hydroxide is the 40 gram per liter is used. And this, and also this will be prepared, that like your the bath compositions. And also the after preparation of the sample, then this will be submerged on your the on to this the NI bath, and before submerging the NI bath, this is the sample is purely submerged into your the palladium chloride solution for the accelerating of your the coating deposition rate. And similarly we can be this will be submerged for your the 2 hours, and after that the secondly this will be immersed for your the NI B bath, that is the nickel phosphorus bath, and also nickel phosphorus bath also the previously prepared according here. That is the nickel chloride is used for the 25 gram per liters. The nickel sulfate also used for the 25 gram per liters. The sodium hypophosphate is the used for 24 gram per liters, and also the sodium succinate is used for your the 48 gram per liters. That is your the temperature range is the belongs the 90 to 90 plus minus 2 degrees centigrade. And also the this is the use for the NIP as the outer layer. And similarly the when the use for the NIP as the inner layer, then this bath is used for the first bath, and also the NIP as the second bath. Another things for the 4 successive layer of the multi-layer, that is the NIB by NIP coatings, and that is the coatings category C are deposit in the dual bath for the 4 hour, and then the altered about here. And this is the few nomenclature about that, and the coating development. That is the 4 type of coating is used, and during to analysis about here. The for the duplex coating, the NIB by NIP, that is the NIB is the inner layer, and the NIP is the outer layer. This is the coating type A, and the coating type B is used. The NIP is inner layer, and also the NIB as a outer layer. That is the coating type B. And in coating type C, that likes you the multi-layer, the NIB is the inner layer, and NIP is the outer layer. That is the 4 layer of alternates. The NIP and NIP coating is used. And another things, that is the coating type D. The NIB is the inner layer, as like as the NIB is the outer layer. The 4 layers of alternate NIP and NIB coating is used. And this is the different microstructural view is find here. That is the first A, B, C, D is the different type coatings, and also you can see like that your the NIB as a outer layer, that is the coating is A, coating is B is here, that is the NIB as the outer layer, and NIP is the inner layer, and we can see like that your the simply cauliflower type of face can find, and this is the different hardness value is measured about that. That is your the different type of coatings we can find, that is your the multi-layer coating, that is the D. When the NIB is outer layer, then this type of coating is the so high hardness value is find. That is your the 1000 above hardness value is find here. That is your the when the NIB is the very hard face is find, and also the for we have to given that is your the NIB is the outer layer, and also during to your the comparison between A and B, that takes your the A is the on NIP is the inner outer layer. For this will be the hardest value is the lower from the NIB as a outer layer for the B. And also the coating C is considered that is the very low hardness from your the multi-layer coating, but NIP as the outer layer, and also fourth successive layer is the depositions about that. But more multi-layer coatings is here, that is your the NI B is the outer layer, that is your the fourth successive layer can be considered about that. This is the hardness value is the higher. And this is the friction performance is discussed about, that is the coefficient of friction is very high for NIP as a outer layer during period the duplex coating, and also the NIB is the outer layer, that is the duplex coating. The friction is comparison between the duplex coating A and B, that is the NIB as a outer layer, then your the coefficient of friction is lower, and also the coefficient of friction is higher from the NI. The four layer is creating, that is your the multi layer. The NIP as a outer layer, that is the coefficient of friction is more, and also the coefficient of friction is the very less from during toward the multi-layer coatings like that NIB as a outer layer. And this is the considered about your the wear behavior, and during toward the four coating types we can see like that your the multi-layer coatings, that means your the NIB as outer layer is creating, then the wear rate is the very low, and also that is your the wear rate is high as like the duplex coating. NIB is the inner layer and NIP as the outer layer, then your the coating wear rate is the very high, and also the wear rate is the reduces from your the NIP as is the outer layer, and also the duplex coating is considered about that. And also the again during toward the multi-layer coatings we have to comparison between the C and D, then we can see that is your the NIP as the outer layer, then your the wear behavior is also so high, and also the NIB is the outer layer, then this will be the wear behavior is the wear rate is the very low. And this is the few conclusions about that. The to study the present works, the following be appropriate analysis led to the following conclusions. The present study reveals that it is possible to prepare electroless duplex NIB by NIP, that is the NIB as the outer layer, and multi-layer NIP and NIB, that is the coating by sequentially dipping into the previously prepared two coating bath. The NIP, that is the high phosphorus, that is your the this concentrate is used for your the high phosphorus content is taken, that is the NI, that high P. The solution may decompose merely due to fluctuation of temperature. That is your the this is the very much difficult to stable in your in this bath. That is a few suppose the temperature is the fluctuate, then your then the bath composition is the decompose on that time. The NIB bath is much more stable without bath decomposition for a period of 2 hours. And the second thing is that that is for microstructural view, it was observed that nickel duplex coatings reveal the uniform coatings and how good compatibility between the layer with respect of nodular formations and grain boundaries. And another here, the high wear resistance is achieved in coating D as compared to all types of coating depositions. Comparison between the two types of multi-layer coatings, the highest wear resistance was observed in for NIB as a outer layer, and lower wear resistance for NIP as a outer layer. For the duplex coating, the NIP wear resistance is higher than the duplex coating NIP by NIB. That is the NIB as a outer layer is considerations here. The hardness of coating C is lower from the all types of coatings. This will be found that like your the multi-layer coating, but this is the outer surface is the nickel phosphorus. That is your the very hardness rate is the low from the all types of coating. It is also reveals that hardness values are lower for coatings A the highest hardness values was found for multilayer NIP decompositions. The multilayer coating, D is most effective coatings of among the all types of coating on the performance of hardness and wear resistance. And this is the references is used to prepare this um, uh, experiments also. Thank you, sir. Thank you, sir.
Thank you very much, Mr. Polas বিশ্বাস, for your beautiful presentation. Now I will ask audience if we have any questions, we can ask to Polas বিশ্বাস. Is there any question? Okay, now Polas, I am asking one question. Okay.
Yes, sir. Yes, sir. Yes, sir.
Either this is totally experimental based, or is there any numerical verification? Numerical validation?
Totally, sir. Experimental based, sir. Totally experimental based.
Total experimental based. Is there any plan to continue for the same numerical validation?
Yes, sir. Yes, sir.
Yes. Okay. Okay. Any question more?
Okay, Polas, I have a question.
Yeah.
I have a question, Polas.
Yes, sir. Yes.
Mr. Polas, that what is the further studies of your this study means project means in future what you do?
Actually, I want to continue. That is your the XRD and few analysis. That is your the characterization purpose, and also the mode same, and also the cross cut, and also the mapping is all things about the further study also done during to this project.
And apart from this, would you like to conduct any design of experiment of this
Yes,
like factorial or Taguchi or other methods with
No,
this?
no, sir. Actually, presently there is the no intention about that. Your the Taguchi utilize your the different modeling purpose, and also the only totally experimental base. And after today is not decide about that, and further my guide is the decide. Then I also consider about the further Taguchi model, and also another model is used.
Polas,
Yes, sir.
under whom concern actually you are doing your research work?
Yes, yes.
No, who is your guide?
Sir, my guide is the Dr. Suman Kallan Das, and also co-guide is Dr. Prashant Saab.
Okay, very good. Okay, now you can continue this work. Okay, but my perception is that if you go for validation, then it will also be better for you. And if any paper is communicated, then it will be very much helpful. Okay.
Okay.
Okay. So probably there is no question from the audience. Now we can proceed for the next presentation. Okay. So the title of the paper for the next presenter is numerical simulation and study of the effects of machining parameters under dry turning condition. The paper ID is MM1574. And Dipanjan Dey, Mr. Dipanjan Dey from the Department of Mechanical Engineering, Jalpaiguri Government Engineering College. Probably he would be making this presentation under this topic. Okay, so I am requesting Mr. Dipanjan Dey to continue your presentation. Okay.
Yes, sir. Starting within a minute. Sir, is my screen visible, sir?
No, not visible. Before that, Mr. Polas বিশ্বাস, you may mute yourself. Polas. Okay, now it is visible, clearly visible. Okay.
Okay, sir. Okay.
Okay, you can proceed. Okay.
Okay. So first of all, good morning to respected session chairs, professors, and one and all present here. I would like to express my sincere thanks and regards to the organizers of the conference and for providing me with this opportunity. So today my topic of presentation is numerical simulation and study of the effects of machining parameters under dry turning conditions. I would like to thank Professor Dr. Nipen Mondal, who has guided me in my research. In industrial practice, the common goal involved in almost all the machining process is to reduce the power consumption and cutting temperature while the machining operation takes place. Simulation and finite element analysis models to study the turning process are an effective way to analyze the effects of the machining parameters. So my statement of the problem is the turning operation, as I have said already, it is one of the most basic machining operations. So the tool life, tool wear rate, cutting temperature, and power consumption by the machine are the major factors which are looked upon in order to increase the efficiency of the machining process. Conventionally, what the route we are taking is we use minimum quantity lubrication, liquid carbon dioxide, flood cooling, etc. That is, we are moderating basically the cutting fluid so as to reduce the cutting temperature. But due to various reasons such as environmental degradation, the cost and affordability of such materials, and also we are unable to reuse it again and again, dry condition is mostly preferred. It has been seen that under dry condition, the very minimum amount of cost and also very minimum amount of environmental degradation is caused. But also dry turning has its different disadvantages also, because it is not very effective in reducing the cutting temperature. So the emerging field of research in this respect is to develop the tool geometry so that the temperature generated during the machining operation is optimized. So the objective of our study is to develop a finite element model by study of the tool geometry first of all, study of the turning process by simulation, whether such a study is feasible or not. That is, we are actually studying the feasibility of simulating such a model. Identification of the heat affected zones. If we identify the heat affected zones actually, then we can develop the tool geometry accordingly so that the temperature can be optimized. And also the cutting temperature and load in turning process, we have tried to analyze that. Methodology in this study is the process setup and controls, that is the input of the machining parameters and setting up of the initial environmental conditions, followed by the tool and workpiece setup, that is positioning of the tool and assigning tool and workpiece material. Here we have used actually the material that has been used is the tungsten carbide for the tool material, and for the workpiece material we have used AISI 1013. Then we go on to the mesh generation, followed by setting up of the boundary conditions and defining the equations. Also then simulation controls and database generation, followed by the post-processing part, which is results and data interpretation. So this is the schematic diagram. We have tried to simulate the model and develop this particular, this is known as the insert. This insert we have tried to develop using SolidWorks, and the mesh generation is also shown here. For the workpiece part, we have taken a significant part of the tool, the workpiece, and we have tried to generate the mesh accordingly. And the tool and the workpiece meshing conditions, as I have said earlier, the tool material is tungsten carbide, workpiece material is AISI 1013, and other elements of the number of elements for tool mesh generation is 45000. That has been found after so many trials that this number of mesh is very accurate and gives us fairly good results. And there are actually two models that has been used in simulating this type of behavior. One is the arcade model and is the UCI model. We have used the UCI model. This is because there are significantly less calibrated constants that are experimentally calibrated. So this equation is particularly useful. For the post-processing part, this is the mesh after chip formation. And this is the effective strain. As you can see, these are the regions that has developed more strain. This is the stress regions. Temperature at work surface and chip. There you can clearly see the temperature variance as the chip cutting goes on. And this is the tool. Here you can clearly see in this part that the temperature starts to rise, and then in the X surface the temperature goes on, proceeds, and here also the same thing goes on. These are the graphs for temperature generated in workpiece versus time. For the different values of cutting velocity, we have tried to vary the cutting velocity. This is for the workpiece, and the next graph, that is this one, is for tool. So you can clearly see that as we vary the cutting velocity, the temperature also varies, which is also in agreement with the experimental data. Is the load prediction curve for the different values of depth of cut. Here we have tried to vary the depth of cut. The first one is for 0.12 millimeter, and the second one is for 0.3 millimeter. These are the settings of the turning operation is in finite element analysis. Here you can clearly see this is the prior settings which you have started, the initial conditions, then the temperature generated at the workpiece in these three, and the material deformation also you can see. The mesh clearly shows that the material is being deformed as the chip formation is taking place. The tool temperature development as it proceeds on to the rake surface. The heat distribution due to wear at the interface. This is due to the wear. Conclusions to show that the different relation and relative dependence between the machining and response parameters during machining help defining the tool geometry and this development according to user defined model, so that the efficiency of the cutting tool and machining operation can be increased. Calculate the temperature generated at the tool and workpiece and show the possible heat distributions. Calculate load, stress, strain, and damage caused. Show the possible wear, tool life, and also other response parameters. The basic model developed can be used for optimization of the temperature and tool wear, and thus reduce the basic power consumption. Also, to find out the difference in the efficiency of turning operations under different cooling conditions, that is in dry turning and application of different type of coolants. Here we can also actually vary the environmental conditions and also the type of coolant used. For dry condition, we have naturally given the cooling coefficients, the heat convection coefficients of air only. So basically it relates to the dry turning, but we can also vary that. Going on to the further scope of research, there is further scope in designing and modeling of the tool to reduce the tool wear and power consumption, study of the chip formation and its geometry, to determine new models for tool wear, to determine models to calculate heat generation and its effects that agree with the experimental results, study the effects of machining under various cooling environments, and also selection and analysis of proper tool and workpiece setup suitable for the maximum efficiency in turning. These are some of the references, and thank you for your patient hearing.
Okay, thank you very much, Dipanjan, for your beautiful presentation. Okay, now I will ask to the members, those who are present in the audience, if there is any questions, then we can ask him. Now I am one question. Now I am taking one question from the chat box. Sir, our honorable sir, Professor Shantanu Das, is asking one question. Dipanjan, what is the range of temperature calculated? Before going to study, you should know what is the range of temperature calculated.
Yes, sir. I will be showing you. Here actually you can see the maximum temperature that has been reached. These are the regions. You can see clearly that the maximum temperature is fairly about 600, and here it is about 180 for the tool. For the workpiece it is 600, for the tool it is about 160.
Is there any question from audience? Probably there is no question. Okay, Dipanjan, I am asking one question.
Yes, sir.
Regarding your study, whether this study is only related with your numerical work, or is there any experimental work is there?
Actually, sir, we have not conducted any experiments so far, but we have validated our numerical results with the different types of data that has already been done. But we are planning to further develop.
How from you have got the data?
Yes, sir.
Without doing experiment, how from you have got the data?
Sir, actually, we have done this using response surface methodology. We have taken a range of the input parameters, and
No,
when we have
you are giving the input parameter, but before giving the input parameter, you have to collect the data now with the help of the experiment,
yes,
or from anywhere you have to collect the data to analysis.
yes, sir, we have actually verified with the different published authors
Oh.
the experimental results, and we have found that it fairly matches with the
That means
numerical.
you are taking the data, experimental data from the renowned papers. Okay.
Yes, sir. Yes, sir.
And to do analysis, numerical analysis, FEM analysis, which type of package is used by you?
This particular platform is known as Deform 3D, and for the tool geometry development, we have used SolidWorks.
SolidWorks. Okay, very good, very good.
Thank you,
Okay.
sir. Thank you.
Probably there is no question. Okay, so we can proceed for the next presentation. Next presenter, I'm able to actually see the actually Suresh Gayan. Suresh Gayan. Suresh Gayan is there? Suresh Gayan? His ID is visible, but probably he is unable to hear me. Suresh Gayan?
Hello, hello.
Okay. Are you getting
Hello?
me, Suresh Gayan?
Yeah, this is Suresh. Yeah, yeah.
Okay, so probably you are having connectivity problem. No. Okay, now the problem is to some extent solved. Now this is your time to present your paper. Where your paper title is Effect of Process Parameters on Force Tense During Friction Stir Welding of AISI 316 L pipes. Your paper ID is MM1570. You are from Department of Mechanical Engineering, Jadavpur University. Okay, now you may continue for presentation. Okay, Mr. Suresh, please.
Yes, sir. Yes, yes. Yes, sir. Is it audible? Hello?
Okay, okay, it is clearly visible. Suresh,
Okay, okay.
you can continue.
So I am in the friction stir welding of ASI 316 L pipe. The friction stir welding is a solid state welding process in which a non-consumable rotating tool consists of pin and solder is used. So during the welding, the tool has been given rotation and a motion. So when the tool come contact with the workpiece, then the adjacent workpiece they have produced high amount of heat, which is actually help to join the workpiece. So that is happen above the recrystallization, but below the melting temperature of the workpiece. That's why it's called a solid state welding. So there have four reasons after if we cut the cross section, there have seen four region, that is the nugget zone, steer zone, the thermomechanical affected zone, and a heat affected zone. So in this schematic diagram, you can see the tool with the shoulder and the workpiece. The various force also has been shown here, the X force, Y force, and the Z force. This is the workpiece material which we have used, that is SI 316L pipe. So L is indicate the low carbon steel. Here you can see that 0.023% carbon. So it's very low carbon, and the chromium percentage is very high. Here 17.40% chromium, so it's a corrosion resistant steel. This grade of steel is also called the marine grade steel, because it's used in marine industries as it has the corrosive properties. So these are the properties of this 316L pipe, mechanical and physical properties. I'm not going details on there. These are some applications of 316L pipe: the food processing industries, oil gas industries, chemical industries, power plant industries, and obviously marine industries, because this grade of steel is also marine grade steel. So this is the tool which we have used for joining the pipe, 316L pipe. So PCBN polycubic boron nitride coated tool has been used, and which is tungsten rhenium shank, and the tool pin is right hand thread over the tool. So the experimental process, a research machine on A.7 with a programmable rotating turntable is used for joining this 316L pipe, and the machine capabilities, the maximum torque is 186 Newton meter, and maximum vertical force, that is Z force, is 67 kilonewton. Maximum X and Y forces are 22.25 kilonewton. So the pipe diameter, the pipe which we have used, that is outer diameter is 272 millimeter, and the thickness is 6.5 5 millimeter. So the welding has been done with a PCBN coated tool, which I have already mentioned. The experiment is conducted in position control mode at constant depth. So the depth was kept constant of 6 millimeter. So the welding, when the welding has been started, so initially the tool position was 3 millimeter above the top surface of the pipe, and the engagement, so the total traveling distance during the engagement is 3 millimeter in air and 6 millimeter in the material, and 1 second was given the dwell time for the extracting. The total traveling distance is 9 millimeter. It was in 50 millimeter per minute feet rate. So this is the setup for experimental experimental. So this first left side picture, you can see that the attachment of the pipe welding, and the second one is the second picture is during the pipe welding. So you can see that become the red hot due to the friction heat. So this is the process parameter which involved in the friction stir welding. So the first three, we have worked on this first three process parameter, that is tool rotational speed, tool traveling speed, and the plunge depth. This is the friction, the set of process parameter. The set of process parameter set was 300 millimeter per minute, 100 millimeter traveling this millimeter per sorry 300 rpm and 100 millimeter per minute welding speed and 6 millimeter penetration depth. So this 6 millimeter penetration depth has been kept constant for all the set of process parameter, and the traveling rotational speed is being varying from 300 to 400 rpm, and the welding speed is varying from 50 to 100 millimeter per minute. Uh, uh, the This is the picture of the pipe welding outer surface and the inner surface of the pipe welding. So we can see that there have no any defect visibly seen here in inside inner surface and outer surface also. So the result and discussion in this is the post first set of process parameter. Here you can see the three different zone: engagement zone, welding zone, and the extracting zone. So for the combination of 300 rpm spindle speed, 100 millimeter per minute welding speed, and the jet force has been achieved 22.46 kilonewton at the start of the welding zone and 22.75 kilonewton at the end of the welding zone. And the X force is varying from minus 51 point minus 0.5 on kilonewton to minus 6.69 kilonewton, and the Y force is varying from minus 2 to minus 5.96 kilonewton at the start and the end of the welding zone. So in this parameter condition, there have not been shown any defects. So the good quality of surface has been achieved in this friction stir welding process. Uh, this is the fourth strain at the second set of process parameter, and here also the spindle torque is varying from 127.2 newton meter to 84.96 newton meter, and the Y force varying from minus 99 kilonewton to minus 2.35 kilonewton. So in this set of process parameter, there has been not any defect by visibly shown. This is the third set of process parameter where the vertical force or jet force is been achieved 43.5 kilonewton at the start of the welding zone. This is the fourth set of process parameter. The vertical force is being achieved at 43.5 kilonewton at the start of the welding zone, and this third set of process parameter and fourth set of process parameter, the force strains, the x, y, and z force, and also the spindle torque is similar kind of trend as given. This is the fifth set of process parameter. The process parameter was 400 rpm, 50 millimeter per minute, and 6 millimeter depth. So in this set of process parameter, the vertical force is recorded 36.9 kilonewton at the start of the welding zone, and there has also not been shown any defect. So this is the comparison of force and the torque with the help of bar chart. So you can see that X force is increases up to 350 rpm. Then it's decrease because why? Because maybe due to the
high heat generation at the high RPM, the material is has become softened, and so for that the X force has less at the high RPM. And for Y force, there have not shown any prominent uh, X comparison of X Y force. And for the Z and spindle Z force and the spindle torque, the similar kind of the value has been achieved. Why here also the force has been increases at maximum at 325 rpm, but after that it has been decreases because the softening of the material, the torque is being reduced. So this already I have described. So this is the conclusion that the variation of the tool force and the spindle torque with welding parameter during the friction stir welding of 3 on 6 L5 under position control mode has been investigated. And the force and torque recorded in different parameter are similar kind of trends in different zone, that is the two engagement zone, welding zone, and the extraction zone. So the steady value of the particle force is in welding zone is observed 20 to 23.3 kilonewton to 29 kilonewton, and the spindle torque varies from 64 newton meter to 84 newton meter.
Suresh, we are unable to hear you.
Depth which we have achieved ultimately.
We are unable to hear you, Suresh. Problem is being arised. Probably there is a network problem. Suresh, am I audible? Suresh, Suresh Gan, probably he is disconnected. Suresh, probably he is disconnected. Okay. Uh, Actually, Sir has asked one question. Hmm. We are taking this question from chat box, but Suresh is disconnected. Okay, so actually we are having we are having actually six papers, but out of six papers, four presenters they have presented the papers, and uh, for paper ID MM1560 and paper ID MM1566, the presenters are absent. Okay. Uh, so we have nothing to do. They are absent. Now let us actually wrap up the session.
Yes, sir. Please conclude.
Okay, let us
I
refer
think
the
the papers are absent. I think they
refer
have
the
absent
session.
already. Yeah. Please conclude, sir.
Okay, okay. Now I'm going to wrap up the session. Probably if the organizers have selected, am I audible? Am I audible?
Yes, yes, sir.
Yes, sir. Yes, sir.
So probably if the organizers have selected the papers with lot of clarity, and the papers, in all the papers, I have gone through the papers as much as I can. Okay, and I have seen that actually in all papers, the authors they have given lot of insights with more understanding between the numerical as well as the experimental numerical as well as the experimental verification. Okay, in order to actually articulate, to understand, as well as to ensure or rather I should say to enrich the all engineering actually community. Now, for the presenters, actually, I would like to say something that actually they have faced a number of questions and the comments given by us. Actually, it will be very much beneficial for their future to continue to their research work. With this, actually, I'd like to conclude, and I would like to express my actually uh, express my appreciation, and also we can show our appreciation to the presenters for their beautiful presentation. Now, actually, I would like to express my also thanks to the audience for their actually beautiful participation. And obviously, I'd like to express my gratitude and thanks to the organizer, those who have organized this kind of beautiful conference, international conference at Jalpaiguri Government Engineering College. And I'm getting this opportunity to be here, okay, to act as a session chair. So, in my deep of heart, actually, I am expressing my thanks to them, especially to Dr. Orijit Kundu, okay, and Noeem Hossain. They are actually coordinator, and Madhav Mandal, he is also the co-chair session. Okay, so this is my actually expression to express my thanks to all of you. Okay, now
Thank
let me
you.
close the
Thank you.
session. Thank you so much.
Please send us the tabulation sheet, filled in tabulation sheet by email or
Okay,
via WhatsApp, whatever.
I have already filled up the tabulation sheet. Okay, now it will be sent
Okay,
to me. Okay, now it will be
okay, sir.
sent to me. Okay.
Thank you, sir, for judging the session. Thank you.
Okay, okay. Thank you so much for giving me this kind of opportunity. Okay.
It's our honor.
Okay, you can continue for your other assignments. Okay.
Okay. So thank you.
Okay, thank you. Thank you so much.